Well, in this lecture, I want to look at some more aspects of the 6-pi and really any electrocyclization reaction. But I want to start with this. I want to say if we have a 6-pi electrocyclization reaction, we should make note that we do have the opportunity to form stereocenters if we have substitution at the end of our hexatriene system. So I can treat this with either heat or light. And because I've got these new groups A and B, after we do the reaction, I'm going to go counterclockwise this time just to continue to reinforce that we could go in either direction. But after we do the 6-pi electrocyclic ring closure, we're going to form a product that looks like this. Because A and B are different from what's in the rest of the molecule, we have an opportunity to form stereocenters. So we can form stereocenters at these positions. Now, what is the stereochemical outcome here? Are these wedges, dashes, that sort of thing? Well, it turns out that like the Diels-Alder reaction, both enantiomers of a single diastereomer will be formed. Now, additionally, because the product is a ring system, we can kind of further narrow down the stereochemical possibilities. So because we form stereocenters on a ring, we can only have cis or trans products. Okay, so we really only have to worry about the relative orientation of A and B with respect to each other. We don't have to worry about whether or not A is a wedge versus a dash, because it could be either. We could form both enantiomers. It's just what we have to worry about is how is A positioned relative to B. If it's always trans, then A, if A is wedge, then B is a dash. They're opposite. And then if the corresponding enantiomer gets formed, which it always does, then if A is a dash, then B is a wedge. Okay, so what we need to recognize is that in a situation like this where we have only two substituents, we're going to form a cis or a trans product. And so we want to be able to label that. Now, it turns out that and I mentioned this before, but a single diastereomer is formed. A single diastereomer is formed, but both of its enantiomers are formed. This is similar to what we saw with the Diels-Alder reaction. Okay, so what's cool about, well, there's a lot of things that are cool. It's cool, in fact, that we can just get a single diastereomer, but another interesting facet about all of this is that if we use heat, and recall that we can use both heat or light, I'm going to just, if we use heat, we obtain the opposite diastereomer that we get with light. Well, that's pretty cool. And that's an important bullet point to kind of make note of. Well, I've always said let's use heat or light, but it turns out that if you can form diastereomers, you'll form the opposite diastereomer whether or not you're using heat or light. Now, that's really kind of profound. I mean, heat and light, they just are energy suppliers, right? Well, on the surface, sure, but the mechanism that they use to actually supply energy to the system is different. So why is this the case? Why do heat and light result in different diastereomers? You might recall that diastereomers differ in every way except for the connectivity of the constitution. That is, they flip some wedges but not all, whatever. But another way of thinking about it is these are very different things. These are different molecules. So why do heat and light result in different diastereomers? That is, different molecules. It's just heat and it's just light. Why are we getting different products whether we choose one or the other? Okay, so to understand this, we have to focus on the frontier orbitals. I should call them the frontier molecular orbitals of the starting material. Okay, I'm going to partially answer this question in this lecture. I should probably cut a break once we get to the, after we finish describing heat. I should probably take a break before we move into a different, and start a different recording for when we go into light. We'll see how it goes. But we can at least partially answer this question. So what I want to do is I want to consider the frontier molecular orbitals of the starting material. The starting material is this pi system. I made sure to draw this central alkene as Z, right? I screwed that up last time. Jeepers. I think in the past I've screwed that up also. I don't know what my issue is. Anyway, neither here nor there, right? You guys are focused on yourselves. It's good. Okay, so the central atom is Z, but otherwise we have an extended pi system, a conjugated pi system with 6 atoms, 3 pi bonds, and then overall 6 pi electrons. The starting material has a conjugated pi system. We've looked at molecular orbital diagrams for conjugated pi systems before. A conjugated pi system. Additionally, we have 6 atoms in the pi system. Why is that important? Well, that tells us how many of these p orbitals we have to use to construct each of the molecular orbitals. So we need 6 of the p orbitals shaded in various ways. And how many molecular orbitals total? Well, if we take 6 atomic orbitals to construct the molecular orbitals, we need to result in 6 overall molecular orbitals. And 6 molecular orbitals. So these 6 atoms that are included within this conjugated pi system tell us how many molecular orbitals we have and also how many non-hybridized p orbitals we have that we're going to use to build each of the molecular orbitals. Okay, what else do we have? Well, we have 3 pi bonds providing an overall 6 pi electrons. So there are 6 electrons in the conjugated pi system. Yes, I know that between each of the carbon atoms, there's a double bond on one side and a single bond on the other sides. But those single bonds aren't what we're worried about right now. We're worried about the conjugated pi system. That's only looking at the pi bonds, those second bonds. So we just ignore the head-to-head overlap, focus on the side-to-side overlap. So we have 6 molecular orbitals. We have 6 p orbitals within each of those molecular orbitals. And what we can do is construct a molecular orbital diagram for hexatriene. Okay, so let's do that. So we're going to have, let's see, need a lot of space. So I'm going to have 1, 2, 3, 4, 5, and 6. 6 lines corresponding with pi 1, pi 2, pi 3, pi 4, pi 5, and pi 6. My nodes, we're going to start at 0 and increment by 1 until we get up to 5. Now we're going to have 6 p orbitals. I'll only make us do this once. All right, so the first one has 0 nodes. So my style is put the shading on top. You could put the shading on the bottom if you want. But there, I've got 6 p orbitals all in phase across the top. Now, for my next molecular orbital, I'm going to have a break right through the center to maintain symmetry amongst the orbital. Okay, so I have a node, one node right here. Now for 2 nodes, I'm going to split this up into thirds. That's only 5 orbitals in this one. Okay. And so what I do is I always just collect myself. So for 3, those 3 are going to be right here, right there, and right there. So our nodes are 1, 2, 3, where we see the color break. And I should have drawn here the 2 nodes for pi 3. Pi 5 is always the highest, pi 6, excuse me. Pi 6, the highest energy one, is also easy because you get the maximum number of nodes. So each time we increase the nodes, we increase the energy of the system. So I just want to, if I have a computer in front of me, I just want to make sure I get pi 5 right. So pi 5 is we just have in-phase overlap in the center. Everything else alternates. Okay, so we have here, 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 here. Okay, so we've hit 4 nodes for pi 5, 3 nodes for pi 4, 5 nodes for pi 6, 2 nodes for pi 3, 1 node for pi 2, and then everything has in-phase overlap at pi 1. Now what I want to do is to the left of each of these, right next to the labels, I'm going to put a line for their occupancy. That is how many electrons we have. So this is going to be the occupancy, or the number of electrons. So we have 6 electrons total. We're going to do here, 3, 4, 5, 6. And so indeed, we cut our picture in half and we get a bonding line and an anti-bonding line. So this is a 0 energy and this is bonding. And this is anti-bonding. This suggests that the pi system is stable and we'll have 3 pi bonds in our system. Okay, that's all consistent with what we see from the molecular orbital diagram, or from the Lewis dot structure, the bond line structure. We see that we have 3 pi bonds. Okay, we knew that. We knew this was going to be a stable system. This is a stable molecule, right? We can put it in our hands. So what's the takeaway from such a complicated drawing that I'm kind of stalling so you all can catch up? Well, the takeaway is that if we look at this, we can now identify the frontier orbitals. The frontier orbitals are the highest occupied molecular orbital, which is denoted as the HOMO, and the lowest unoccupied molecular orbital, which is the LUMO. So the HOMO is pi 3. That's the highest energy orbital with electrons. So if you look at the 3 orbitals with electrons, pi 1, pi 2, and pi 3, they're all bonding, sure, but the only one that's highest energy is pi 3. The LUMO, the lowest energy unoccupied orbital, is pi 4 then. And so the gap between the HOMO and the LUMO is defined as pi 3 and pi 4. Okay, so what we've done is we've indicated the frontier molecular orbitals for hexatriene. And I say this is critical to understanding the stereochemical outcome in an electrocyclic ring closing reaction with hexatriene. Okay, so what I'm going to do now is scroll up. So this is kind of like a spoiler alert system. Pause if you need more time here. So what I'm going to do is recognize again that the HOMO of hexatriene, gosh, Z is pi 3. Pi 3 has orbital shading such that we have 2 nodes, and that's just kind of having thirds within our picture. So we can get the 2 nodes. Okay, so what we're going to do is consider sort of a 3-dimensional picture for this. So let's consider a 3-dimensional picture where we allow the molecular orbital to be overlaid into the structure that actually reacts. So what I'm going to do is I'm going to draw my hexatriene like this. I have double bonds here. And if we needed to, we could draw some arrows to show the formation of product by way of a 6-pi electrocyclic ring closing reaction. But instead, what I want to do is focus on the orbitals. I want to focus on the orbitals, namely the highest occupied molecular orbital. So it starts shading up for the first 2 orbitals, then in my approach, shading down for the second 2 orbitals, and then shading up for the last 2 orbitals. Okay. Now what I want to do is I want to rearrange the electrons such that I make a new sigma bond between these starred carbons. I should star those in different color ink so you can see them actually. So the new bond forms, and it's not just any bond, it's a sigma bond with head-to-head overlap. The new sigma bond forms between the 2 carbons with stars. Okay? So between C star and C star, how do we get head-to-head overlap to occur? Well, what we need to do is have in-phase overlap of 2 orbitals that were once p orbitals. That is, I want to take this lobe and overlap them, or I could always take this lobe and this lobe. They have to be in phase, so I can't have dark matching with light here. That would be considered out of phase because the signs wouldn't, they would add up in a destructive manner, not in an additive manner, okay? So what we need to do is figure out a way for this molecule to accomplish overlap that's in phase between those 2 orbitals. Well, it's actually quite intuitive. What we do is we picture them sitting straight up like this, where my fists represent parts of the orbital that are in the same phase. And all we do is we let them rotate into each other so that they can overlap. I can't overlap my fists, right? But so we can allow orbital overlap to occur. So they just need to rotate. Now for them to rotate, one needs to rotate one direction, one needs to rotate another direction. On the paper, what that looks like is that we're going to have, and I'm going to have a thick arrow here, we're going to have this orbital rotating clockwise and this orbital rotating counterclockwise. So we say orbital rotation occurs. And once we have orbital rotation, I don't really care about the rest of the orbitals at this point. I mean, we could just draw the two double bonds, but I do still care about these orbitals in the center here. Now we have in-phase overlap here. So we could have gone that way, or we could go opposite rotation. I'm just going to write or here, because opposite, we'll see in a second, is not going to be super helpful. If we went the opposite direction, what I'm saying is the light phases could overlap. So we could have in-phase overlap of the two dark phases or in-phase overlap of the two light phases. Okay. Now, what's interesting about this is that each of these results in a different enantiomer. So each approach results in a different enantiomer. And if you're like, wait, stereochemistry? Why is stereochemistry getting involved here? Okay, let's now go back to our original case and start to add some substituents. What I want to do is add A and B. So the original case was this hexatrine, which we're saying undergoes a 6-pi electrocyclic ring closure to give rise to A and B, where we have these stereocenters at each of these positions because A and B are different. Okay. What we should do now is apply A and B to our orbital schematic up above. Okay, we don't need to draw all of the orbitals. We could draw the homomolecular orbital in its entirety, or we could just focus on the ends, the terminal orbitals. So in this case, the terminal orbitals are actually identical, right? So what we need to do, though, is we need to draw my hexatrine double bond. We need to add the substituents, and we're going to have both of them facing out, right? It's like both of them are pointing out in the, gosh, how do I do this? Okay, both of them are pointing out in the original structure, and then I'm just kind of rotating them out this way, so they're kind of facing us now. Okay, I really like the thumbs. So what I'm saying is we're sticking them out like this. Okay, so they were like this when we had it kind of oriented, I don't know, side view, and then when we go front view, they look like this, and they're both sticking out. This maintains an E geometry. Maybe I beat that into the ground and you got it right away. I don't know. So anyway, we maintain an E geometry across both of those alkenes, Z in the back, of course. But what we need to do now is do our rotation, and I'm going to pick on the rotation to put the dark phases into in-phase overlap. Okay, so all right, so we roll these orbitals into each other by having one go clockwise, which is on the left, and the other one go counterclockwise. And then the outcome there is a structure after the reaction has occurred where if we, how do we picture this? Well, if I take my thumb and I stick it out and I roll one, in my view is clockwise, that might be counterclockwise too. If I roll one this way and one this way, they're both going to stick up. Okay, that is, let's think about it this way. Oh gosh, this is hard. Okay, here are my palms are the orbitals. These are the dark shaded orbitals that are about to roll into each other with in-phase overlap. My thumbs are A and B groups. What I need to do is roll my hands so that there's in-phase overlap. Now what happens to my thumbs? My thumbs were A and B. Now they're both sticking up on the same side. If alternatively, oh gosh, I don't know how to do this. If alternatively, I had a group pointing inward and a group pointing outward, and I rolled them into each other, now one would be up and one would be down. This would be a trans relationship, but what we have is something like this, where we roll the orbitals into each other, fingers interconnect, sigma bond is formed, but now the thumbs are pointing up, so they're both on the same side, and we would say that's cis. Okay, so A and B spin with the orbitals. go up this way and up this way. And as a result, A and B end up on the same face, the same side. So we say they are cis. So the outcome that we get is A up and B up. A up and B up. Or the enantiomer, because maybe you're like, wait, how did he roll that in so he got the both of them being up? Or you could have the enantiomer where A and B are both down. Both enantiomers are formed. And if one enantiomer comes from in-phase overlap of the dark phases, you could have the opposite enantiomer being formed by in-phase overlap of the light phase, the light orbitals. Okay. So that is how we get our orbitals to overlap and our groups to actually find position due to the frontier orbitals of our system. So in this case, just to recap, what's happened here is during electrocyclization, the terminal orbitals of the starting material's highest occupied molecular orbital rotate such that in-phase overlap occurs. Such that in-phase overlap occurs. That is to say that we just rotate so that whether or not we have light on top or dark on top, we're going to rotate so that the orbitals have in-phase overlap. And we could have rotated one counterclockwise, one clockwise, or one clockwise, one counterclockwise, either iteration, just as long as we find a way to get the in-phase overlap to occur. Okay. Now, this brings up an important term called disrotatory rotation of molecular orbitals. In disrotatory rotation of molecular orbitals, the atoms that form the new sigma bond rotate in opposite directions. That is to say, when I say opposite directions, I'm referring to one goes clockwise, one goes counterclockwise. And what's interesting about that is that's opposite of what we see with light. With light, we go opposite. And just to connect this to the next lecture, which I believe is lecture 55, kind of committing to an order here, but of course, is we would get into what's called conrotatory rotation. So light's going to go in the opposite, and we're going to look at that in the next lecture, but I want to connect the definitions across both lectures So I'm going to write it here and then start the next lecture with this. So conrotatory rotation, I guess I wrote that. Let's keep some parallelism here. So this is the opposite definition. So conrotatory rotation of molecular orbitals. Here the atoms are going to rotate to form the new sigma bond by rotating the atoms in the same direction. So atoms that form the new sigma bond rotate in the same direction. That is to say, if it's the same direction, they both go clockwise or they both go counterclockwise. Both clockwise or both counterclockwise. Okay, so we introduced some new terminology, conrotatory and disrotatory. Disrotatory was applicable to this system as I had it drawn. And I said that what we're going to do is use the HOMO, the arrangement of the shading, I guess, of the HOMO to dictate how we're going to spin the atoms. And it's how we spin the atoms that determines the stereochemical outcome for the electrocyclic ring closure. Now, what's interesting is that, okay, we've got the HOMO in front of us, and we see the orbitals, and we spin the orbitals so we get in-phase overlap. But why then is it the case that light results in the opposite everything? Light's going to result in conrotatory rotation instead of disrotatory rotation. We're going to take our things and spin them in opposite directions. That doesn't appear to result in in-phase overlap. So we'll look at why that's the case in the next lecture. And what it has to do with is that we're actually going to change which orbital we use when we have light being provided as the energy source. Okay, there's the hint. We'll start with that next time. So until then, I guess I will see you next time.